So something that you have to deal with when you do the post-hoc testing in ANOVA is the problem called multiple testing. So here's a cartoon sort of illustration. So someone suggested that jelly beans cause acne. So scientists are going to investigate. So they found no link between jelly beans and acne. The P was greater than 0.05. You can't reject the null hypothesis that there's no connection between them. So that seems simple. But then someone goes, wait a minute, maybe it's because of colour. So they look at purple, brown, pink, blue, teal, salmon, red, turquoise, magenta, yellow, grey, tan, cyan, green, mauve, beige, lilac, black, peach and orange. And almost all the time, nothing happened. The p-value was bigger than 0.05, there was no significant link. But for the green ones, the p was less than 0.05. That was an interesting result. So now they can run out and say, green jelly beans are linked to acne. But the problem is, here you've carried out 20 tests. And a p-value of 95% confidence p-value means there's a 5% chance of getting it wrong, which is 1 in 20. So if I do 20 tests, on average, one of them will give me a significant result, even when it's not significant. This is the problem called multiple testing. So we want to have a confidence level of 0.05 over 20 tests, one of them will give me a false positive. If I was going to do 20,000 parallel tests, I'd get 1,000 false positives, 1,000 things showing up as being significant when a lot of them aren't. It'd be more than 1,000 because you'll also get the true positives mixed in with them. So you have a difficulty of how can you deal with this. So one way, and the most conservative way and the simplest way, is called Bonferroni correction. So Bonferroni correction says if you're going to carry out n tests, you're devising the confidence interval for each test will be alpha divided by n. So if I'm doing 2 tests, you have to split that 0.05 across 2 different tests, so it becomes 0.025. This means you're less likely to reject the null hypothesis, more likely to accept it, but it's very conservative. Means that if you have lots of tests, it's going to need incredibly strong evidence for you to say that there's a genuine difference. It's useful with relatively small numbers of tests, so maybe up to about 20. Beyond this, you need to think about other correction methods. Depending on the field you're in, there could be other methods that are suggested within SPSS. It's just a question of using a click box to pick whichever you prefer. There's also Schieffer's method and Tukey's. There's lots of other methods that you can consider. Bonferroni is by far the easiest and the easiest to calculate what the correction should be. Now, if you're doing very, very large numbers of tests, then you're going to end up with a significant number of false positives if you do the without correction. But if you use Bonferroni, you're almost never going to have a strong enough evidence to find some sort of significance. So you need to take a more pragmatic and balanced approach between these two alternatives. You need to correct for multiple tests, but you don't need to be as conservative as Bonferroni. This led to the work of Benjamin and Hochberg, which means they allow what's called a false discovery rate. So you allow, let's say, 5 or 10% of all of the results you get to be wrong ones. Not all of them will be, but some of them will be. So this allows you to test for things like genes, where you do genetic tests where you're looking at 30,000 genes, and it's called the false discovery rate.